So, is there probably, oh, you see nothing and you say nothing. There are two for nothing. Okay, so Izar already talked to you about systems, and he likes to teach systems first and then filters, but I like to teach it differently. I like to start with talking about filters and then to teach systems, because systems are commonly used for filters, okay? So I don't like to use it as an intro, but rather as one of the applications of filters. So in this recitation, what I want to do is to have like a kind of a short intro to our class. And we will use also this intro to better understand what we are doing in practically. Now, what I wanted to say that there are some mathematics that I won't go into too much details, and Izar will talk about more. Okay, and I'll really try to let you know. So, do you remember what is the Okay, so first of all, we want to understand the uses of filters in neuroscience. So one of the main things that are still studied in neuroscience is, for example, sleep and the uses of EEG. And for example, when we want to see that someone has a healthy sleep, we are looking for two kinds of waves that should be in his EEG. The first one is the K complex, and the other one is the sleep spindle. For example, when people are going to check that everything is okay with them and that they don't have a neurological problem during the sleep, so they are going into sleep lab. And they are being put with an EEG that looks for this kind of phenomena. And now we can see that we can try to describe these two phenomena, okay? But it is very hard to see. We'd rather have a machine that could find each one of them. And how do we do that? So we see here that one of them is a very fast change, right? The K complex. I'm sorry, not fast change. I meant to say that there are differences in the frequencies between them. Which one has a higher frequency? The spindle, right. So this one has a lower amplitude, but a very, very short frequency. And this one has a high amplitude, but this one is slow frequency. So what we're commonly doing is that we take this EEG and then we use a Fourier transform to look at it at different wavelengths, okay? So what we're trying to do, so we take this full EEG recording, we take it into a device, and this device uses the Fourier transform, and then he says, okay, at 0 to 1 hertz, this is the wave that I see. At 1 to 4 hertz, this is the wave, and here the sigma is 12 to 15 hertz, this is this one, and of course, you see over here, we see the spindle, right? This one is the spindle at 12 to 15 hertz, and this is impossible to see it here due to the noise. So only when you filter, you can see that. So what we understand that filter is doing is that we take the signal from the time domain to the frequency domain, and then we take it back. Now, these two transformations, they are problematic, okay? Because we will see in a minute that due to some of the mathematics of the transformations, forth and back, we have problems that we get some things that are not real in our data. Let's see.
Yeah,
Yes.
the signal and the gate complex are representatives of disorder neurological.
And not of a disorder, but when there are lack. So I know that this might mean that you have a problem. I know that this is still an open field that we don't really know what are the reasons for their existence, but we know that when it is normal, you have problems. Okay, so I'm thinking about it's talking about Davis. 1 minute. Yeah, okay. So commonly, we have these filters that take our signal, and when they transform forth and back, they put it at different bands that we use. I talked in previous class about the gamma band, the theta band, alpha band, all of these commonly used bands. But I want to show you a very, very deductive work that was done by engineers in this field. That they were studying they wanted to study the spontaneous activity of the brain. You know what is a spontaneous activity? This is activity that it is not governed by any task or any stimulus that the subject sees or something like that. In fMRI, sometimes it is called resting state, but it is not exactly the same. So it's been a long time since someone really opened this black box of using specific filters like automatically. And then in Davis et al. 2020, they wanted to see the real raw signal. So instead of taking specific bands and filtering to them, they created a power spectrum of the signal that they recorded. And maybe you remember that the power spectrum shows you the relation between the amplitude and the frequencies of your signal. And what they have found, you can see over here that in the raw LFP signal during spontaneous activity, you can see that most of the amplitudes are at very low range, not of 1 to 2 or 12 to 30 or something like that, that this is like given in advance. Instead, they open and they say, okay, I see the power spectrum, and in this spectrum, I see that the right thing to filter is 5 to 40 hertz. Okay? And also, for example, in your project, in project 4, you will be asked to filter a signal in your data. So this signal is the heartbeat. It is given from Hamutal Lab. She allowed me to give you the real data that we use. And in this kind of data, we have an artifact of heartbeats. So how are you going to find this heartbeat? You are not just going to say, okay, heartbeat is 3 hertz, let's filter 3 hertz. No, you're going to create the power spectrum of the signal and see that you have a very high power at a specific frequency that you are not interested in, and then you create the right filter for it. Okay, so this is something that I want you to remember. This is something that is not commonly used, and it should be much more used. You really need to justify your filtering, okay? So they created this 5 to 40 hertz. And then they had, at any given window, they had, okay, the general phase is not that important because we won't talk about it. So what we can see here is that their filtering is here, never mind about the colors. You are not interested in that. And you can see how good is this filtering in relation to the original signal. That it really captures the signal itself and not just filtering to something that you don't really know what is the relation. So for example, if you take the commonly used bands of theta or alpha or something like that, so you can see that there is almost no relation between this filter and the original signal. Okay?
How can we see it?
So do you see here the dots? I'll make it a bit bigger. So you see that this looks like it almost has nothing to do with the original signal. And here they really capture the exact band to use for filter.
It's because it's similar the original one and the color.
Yeah, you can see that this one really goes with the signal itself. Yes.
So global phase means finding that area, that spectrum where you have just the biggest values.
The global phase is something, is another thing from their paper that I don't want to go into too much details, but the idea that they say that you don't just go and say, okay, I know that there is something that should be at the theta wave. You first open your power spectrum, you look at what frequencies are most dominant in your signal, and only then you narrow it, you filter it.
Oh.
Yeah.
I'm not sure how did I know to use the filter for the 5 to 40.
So you could see over here.
Okay, so I
So
understand
you
that.
see that the amplitude is much higher
Okay,
over here.
okay.
So for this reason, another way to do it.
Yeah, but I understand that it's much higher, but what else? I mean, so it's high, so it's higher. Why do I want to?
Okay, so another thing that you might do is using something that is called shuffle. This comes from statistic, a permutation test. So what you can do is take your values and just shuffle them all along your frequencies. And then you do it again and again and again and again. And for each shuffle, you perform this power spectrum. Okay, and then what you will have, for example, in black, the real power spectrum, and in gray, the shuffle one. And then you can look, when do you have a significant difference between your real signal in black and the gray one?
But why do I want to filter the 5 to 40 hertz? I mean,
I think what he's trying to say is if you go down to the other
Yeah.
spectrum, no, the other plot,
Oh, sorry.
it's as far as I understand, it's like you want to have to capture the bigger amplitudes. That's why you're getting only the values where the y-axis on the other plot is the highest, because you want to capture that, like you want to model the bigger, the very tiny oscillations, the kind of like noise
Yeah.
is gonna only show in the right side of that other upper plot, because it has lower amplitudes, so you don't want them. So it's kind of what's moving in a way, right?
It's
It
not
is-
only kind of smoothing,
it's moving, but
any filter is smoothing the data. Any filter, by definition,
Mhm.
and this is something that was about one of the next things that I wanted to say, that is we talk with you about it more, but any convolution or any smoothing is filtering your signal.
And I have a question about that. So when do you know where to cut off, like in the other plot, now in the
Yeah.
upper plot, where do you know it's like, oh, this is a high frequency,
Right.
you know?
how do you know that this is not the actual signal? I mean, how do you know that the 5 to 40 hertz is the actual signal?
This one is just the noise. How do you define it? So I think that
No,
So-
wait, I think I don't understand. This is the spectral analysis, right? This
Yes.
is the frequency and its amplitude, right?
Yes.
Correct? So how do you know if you want to filter 5 to 40 hertz? I mean, just based on the high amplitude.
So so the best thing to do, okay, if you have a high amplitude, this means that this is a dominant component in your data, right?
And how do you know that it's not the actual data that I mean,
over here, this is not the actual data.
No, but the high amplitude is not the actual.
It is the actual data, so they wanted to filter it to keep the actual data as it is.
So when we see.
So
They
Yeah.
wanted to clean the noise.
so when you say that you filter from 5 to 40, you don't mean that you exclude, you mean that you keep the 5 to 40.
Yes, yes, yes.
Okay.
Yes. Okay. And I thought that you're asking, how do you know that the cutoff is at 40 hertz, right?
That was
So
it.
how do you know that? So here we are going into statistics. So the best way to do it, and this is called a permutation test, okay? So a permutation test says the following. So if you have a vector and you have a value here, 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 and so on, and then you use this vector and you perform the fast Fourier, the discrete Fourier transform for this vector, okay? And you got some possible frequencies and so on. Now you are shuffling all the data here, which means that you take this one here, this one here, this one over here, you just shuffle all of it. So you have a random recording, right? If you shuffle, this means nothing. It should, every time you shuffle, you randomize the relation between the data samples. And then you perform another DFT on the shuffle. Okay? So you have the real DFT and you have the shuffle DFT, right? And then you need two distributions. So for example, this real DFT, you take 1,000 trials. That for each trial you perform its DFT. And here in the DFT of the shuffle, you shuffled for 1,000 times. Okay? And then you make a specific statistic test for between them. And for each frequency, you see if you got something significant for the real DFT that you don't have for the shuffle DFT. So for example, in 2 hertz, this one had a very high amplitude of at 2 hertz.
Something significant is high amplitude in a specific frequency.
No, it means that, for example, this one had a high amplitude with a value of 8, okay? And at the shuffle, you got a different distribution at, let's have even higher, 60. So this is significant. Or you had a lower distribution at, it couldn't be minus, at 2, okay?
So it means significant difference between the distributions.
Yes.
And what does it mean to have 1,000 trials in the real Fourier transform? Does it mean 1,000 vectors?
Yes. And for each one, you perform the discrete Fourier transform.
Then for the shuffle, you would have 1,000 shuffles per vector, which would be 1,000.
So it depends. You might have, as you said, a billion. So 1,000 times 1,000 is a billion. And another possibility is that you just shuffle once each one of them. Yeah.
I guess I didn't quite understand. The shuffling that's happening is in the raw signal or in the power spectrum you're moving out?
In the raw signal.
Okay, segments of the raw signal.
Yes.
Plot. Okay.
Exactly.
So
Okay,
in
yeah.
the spectral analysis, we want the high amplitude to be as a signal, right here.
So the reason that I show you this is that you want to know what you want to leave in your, what are the frequencies in your signal. So before you're filtering, look at your power spectrum and then decide and see if it's reasonable what you took for filter. And then you can get, I think that this is a very, very good work because over here, they got a very good filtered signal, right? That they didn't get when they used these types of filters that are more commonly used in neuroscience.
Yes, but what I'm trying to figure out in the first figure is how do we know what to filter? And what I understood is that in this case we took the highest amplitude to be the signal, which was 5
Yeah.
to 4 hertz, and what was not high amplitude
Is
was
this
noise.
one. So for example, in your project, you have just the other way around. I gave you real data from our lab that has a very strong artifact of our heartbeat. And then you need to filter this heartbeat. So over there, the heartbeat will be the strongest, while all the other frequencies will be much lower. So the answer to your question is that it depends on your research question.
Okay, so basically we don't want the highest amplitude, so it depends on what we are looking.
Yes.
Okay.
Yes.
Filtering the heartbeat or filtering out?
Filtering out the heartbeats. Okay. So this is about filters, and here one of the nice things that I wanted to show you is that I'm wondering if I want to talk about it. Maybe I'm doing. I'll go back to it after we will speak about something that is called phase locking, and this is only in the next class. Okay, so now I want to know what are the different types of filters, and as I said, this is something that I'm not going too much into details, but what you need to know that each filter is a convolution, okay? Because every time we multiply something at the frequency domain, this is like convolution in the time domain. Okay, so for example, this is how we plot a filter. So over here, notice that the x-axis are frequencies, not time. And then we want to perform one of the basic for computations. So the first possibility is to perform a low pass. What does that mean? That we said that the lower frequencies are the frequencies that we want to keep in our data. So we have here the pass band. This is the frequencies that we want to keep in the data. We have here the stop band, and in between we have a transition band. So when I multiply this filter by the power spectrum, this will emphasize, this will leave me only the pass band, will erase the stop band, and in between it will decrease the other frequencies. Okay?
The transition.
Exactly. Now we will talk in a minute about the transition, because the transition is very, very important. As you can see here, you see that in all the filters, you don't have a straight line, right? And Isal will compute with you what happens. Oh, we computed already. What happens on the straight line? Do you remember that from last class? When we had this rectangle filter, do you remember that? So we computed its Fourier transform. Do you remember what happened when we computed that? I'll show you. Yeah, the same function, exactly.
Great way.
Exactly. So when you have this transient change in frequency, which is called a rectangular filter, it creates this, they are called ripples. These are non-real frequencies that are going to be added to your real signal due to the fact that you use a filter without the transition period. Okay?
So the transition period has to be not like this, but
So if you do it more gradual, then you will have less filters. But you will always have a problem of ripples in your data. Every time you filter, you will have this problem. You cannot uh, you cannot delete the ripples in any way. Yeah.
So if you just add, how, like, like maybe you'll tell us, what's the minimum transition you need to not have ripples? Is there such a thing?
Okay, so here you can see in a minute I'll talk more about this kind of filters. But you can see that depending on your power spectrum, you choose which type of filter to use. It depends either on your power spectrum. Let's say, for example, that in your power spectrum you have kind of these two populations. One of them which is very low and the other one which is very high. And then if you take, for example, this one over here, that you see that it has a lot of ripples, right? This is the rectangular one. So since you have a very high population over here, and you keep it, and over here you have also another population, so that these ripples will make the most changes at the other. What happened here? I didn't do anything. You know what? Let me go back to it in a minute. Let's first just go again through all of them, okay? Because this is a very complicated film. Not that complicated, but this is one of the more confusing things about it. So we said that there is this low pass. Band pass means that we are interested at the specific frequencies like we had before in the theta, alpha, sigma, and so on. High pass means that we are interested only on the higher frequencies, and band reject. Okay, this means that we want to erase specific frequencies, and this has another name. Sometimes it is called band stop, and another way is notch filter. A notch filter, it's like that you want to erase a specific frequency, only one. It's like a delta function filter. Okay? So this is about it. So now let's be on focus and really try to understand this idea of the transition there. So, as I said, since when we use a filter, right? So here the x-axis is for time instead of frequency. Okay? So what you see here that we have is a rectangular filter, which is this filter, and we can see only its positive part. Okay? And we can see that it creates these ripples, very high ripples, which means that if we have a signal over here, the signal will be decreased, other increased, and we will have changes on the higher population, okay? But let's say, for example, that in our power spectrum, almost all of our data was just here, just by the lower frequencies. In such a case, it won't be such a big deal to use the rectangular one because it won't make so much changes. But other possibilities are, instead of using this strange looking filter, is using some equations that were built by Hanin, Halser, Hanin, Chebyshev, and so on. Some of them you are going to choose yourself in the project. And each one of them has a different ripples pattern. And you choose this ripples pattern based on your spectrum analysis. Okay? Now, this type of filters are not filters that are created, like here. Over here, what you do that you take the frequency and you create a function in the frequency domain. This is what we see here, right? So you say, take a function of f from 0 to 3 will be, it will be equal 1 for the frequencies of 0 to 3. It will be equal 0 from 4 to 10 for bigger than 4, and f bigger than 4. And over here, it will be a linear of minus f when f is between 3 to 4, 1 minus. Let's see, we want to go from 1 to 0 increasingly, so we need it to be linear, right? So it needs to be minus f. And since it is between 3 and 4, so
minus f.
what?
It's just minus f.
But if it is minus f, then at 3 it will be minus 3. So we want to add a DC, right? We want it to be higher. Do you understand our engineering?
Yeah, but
So we need to start from 4.
yeah. Mhm.
Yeah,
No,
we need to start from 4.
don't we need to start from 1?
We want it to start from 1. So when f will be equal to 3, then this will be equal 1. When it will be equal 4, this will be equal 0. So this is the function that we create. So we look at the frequency domain, and then we create a function, and we multiply by this function. I'll just give you an example that I had in a real life example. Yeah,
That's time, right?
that is no. This is the frequency domain.
And what did you say we have to do with this function?
So we create a function, and you can see here examples for functions that we create in the frequency domain. And then we multiply by this function. Okay, we take the spectrum, we took the signal, we converted it to the spectrum, then we multiply by the filter, and we do the inverse of the Fourier transform. This is the idea.
Like doing a filter like this.
Yes, this is called a spectral filter. So I'll give you an example. In our research, we have a very, very irritating monkey that likes to drum like this. Now, this is super problematic because when he drums, it just moves all of the system. And then you have an artifact of drummings. And we cannot take care of these drummings. So I had one of the practical students that was with me asked me, okay, let's take his power spectrum. We know that we can compute the exact frequency of the drummings, which is around 6 Hertz. And then he said, why not just delete it? Okay, let's go and just wherever you see the frequency of the drummings, that it is 6 Hertz, just assign 0 and then take it back to the time domain. And he felt like he's kind of discovering America. And then I told him, this is not a good idea because then we will have ripples. So this is just about, so the ripples are every time that I delete a frequency, I create other frequencies on the time, on my signal. So this is the reason why it was not done. But this is the problem when we want to design a filter in the frequency domain. We don't know what will be the outcomes of our designing, what will be the ripples in our data. Okay?
In that case, what would you have to do? Check all of the filters and see if one of them has less ripples?
Yes. Which one is the one that is matching your data? And in the end, this is what we did. We just went together through all of these filters, and I think that we found that Chebyshev 2 was the one that was relevant for our data. But you can see that still, for all of these filters, we still have these ripples.
What exactly the y-axis is?
So here the y-axis is the, 1 minute. This is FIR filters, this is. I told you that this is time domain, right? So sorry, this is not the time domain, this is another spectral, yeah. This is another power spectrum of possible filters. So this is how the filter looks like. This is power and decibel.
That's why you said that in the higher frequency, there was a little change, right? It was
Yes.
Sign, but frequency.
Exactly. Sorry, yes.
So is there any way to predict what frequencies will be most effective or what ripples we might generate, or is that just not possible to know until after you've done?
So now we will see how do we do that. We have a way, this is called an impulse response. So the difference is that the upper types of filter are designed, but when you look at the frequency domain, and the lower kind of filters is designed by a different way, which is called systems, okay? Which are filters that are called FIR and IIR. And here you have a few tools to view your filters. In this kind of tools, you just click on a button, and then you can see the both in the time and in the frequency domain, the different types of the filters. Okay.
Can you repeat what's the difference? Because you said overtime filters, what is that? Overtime filters versus FIR and FIR.
Yeah. So the upper one are based on the spectral response. Okay. What it does in the spectrum, in the power spectrum. And the lower one are designed differently. They are called FIR and IIR filters, and now I want to start talking about them.
What is,
Yes.
can come back, what is then the x-axis? I mean, it doesn't just the frequencies, right? Because you have like 5,000.
So
I mean, I don't understand it.
Yeah.
What it means.
this one
I
is
see
the
ripples, but-
frequency, yes. This is an example of filters that want to make a cut at the same frequency of 2500.
Okay.
And each one of them looks like this in the power spectrum. These are the ripples that it creates.
And if, for example, we know that we don't have in our signal frequencies that are higher than 200 and
Then-
2,500.
Yeah, so you don't have a problem. It doesn't matter which one will you use. The only difference will be how fast they will work.
Okay.
And by the way, these filters are not only digital, I forgot to say that. They are also analogical. It is the same problem also when you perform an analogical filter. Do you know what I mean by analogical? This means that in electronics, you have different devices that they are creating this effect of filtering specific frequencies. So for example, you have like a specific kind of a gate that opens or closes whenever there is a specific frequency. And when there is this frequency, it closes it, and so on, okay? So there are mechanic devices that can filter the analogical data, not the digitized one. And they have the same problem, Okay, so you should know that this problem of ripples is not only due to the fact that our data is in quantized. It's digitized. It's also true for analogical filters.
The digital filters would be FIR and analog.
No, the FIR and IIR could be also for analogical filters.
Both.
Yes. Okay, so let's see an example for low pass filter. So we have here a signal that was built by combining together specific known frequencies. Okay, so we have here the frequencies from 0 to 30 and from 50 to 80. And when you combine all these sine waves together, you have this type of response. Okay, you just add them to each other. So you have at the 10, 11, 15, and so on. So you create sine waves and you attach them to each other, and then you have this type of signal. And now, when you want to filter them, so you can see over here, we have the filter over here, which is a low pass filter, okay? And in this low pass, you keep only this type of filters over here. So when you multiply this filter by this filter, you are left only with this frequency. And then when you perform the inverse of the Fourier transform, you get this signal after filtering.
You
Okay?
said two types of filters. The orange was low pass.
No, this is the filter. This is the low pass. You keep only the lower frequencies and you multiply it by the signal.
Ah, okay. You said filters. Okay.
Yeah.
So together it's a band stop filter? We have
So
low and high regions?
I think that there is a mistake over here, and this is one of these aliasing effect. It should have been only until 40. So I think you just don't have the higher frequencies, right? Because we don't see them here. So it should have been just until 40. So you can see the relation. What I wanted to show you is the relation between this signal and this signal, right? So you can see over here that we had these really small fluctuations over here. And after they are filtered, you have a much more smooth a signal, which now has only the relevant frequency that we wanted to keep. Okay? And here you can see both of them together on the same graph, and you can see again this smoothing effect. Right, so I just want to remind you, we were talking about convolution bit ago. It's been some while, and we remember that every time we convolve, we create a distortion to the edges and to the time. Do you remember that? And here you can see that from another perspective, that the filter creates this problem of distorting the time, also due to the fact we have these transitions back and forth through the frequency and time domain. Okay? Yeah.
Where did the ripples go here? There were ripples above, and now the orange is exceedingly smooth.
Yeah, so we don't have a ripples because this signal is not a real signal. This signal was built by sine and cosine function. So you had this plus this plus this plus this. So you kind of erased some of them. And then when you, so all of this example is just a kind of design in the frequency domain. And then you get it back to the time domain. So this is an artificial example. This is not using real data.
Okay, but the bottom right, which is also the artificial data,
Yeah.
and it looks kind of bumpy. And then on the bottom,
I think it's just the frequencies. And you don't see it maybe because of the scale.
Ah, so you say that this one,
I think it's because of the scale.
no, he says that it looks like these frequencies are missing over here, I think. Yeah, there's a chance. So you think, oh wait, that this one is more stretched? No, it's the same
But
time.
even the amplitude, like,
Yeah.
it goes up to 15, and it's not going up to
Yeah.
15.
Yeah,
It's not the same thing.
you are right.
So just,
So maybe this one is just this, yeah. Probably there's just a mistake over here.
The amplitude.
It was,
The amplitude should be the same in time and frequency, right?
The amplitude, unless it could be, yeah, the amplitude or the power, it
Mm.
depends.
in the legend, it says the inverse is multiplied by x, what does that mean? Or,
Yeah, so I'm thinking,
multiplied by-
yeah, so these are the multiplication of these two, so
Oh.
this should be here, the same as here. But they do look different. You're right. Okay. So I said that, again, this was an example of how you can design in the spectral, in the frequency domain. And now I want to talk with you about another way to design filter, which is the way of using systems, okay? And this is one of these kind of questions that Izar really likes to ask because it is quite new to most of the students. So I want us to fully understand the idea. I'm wondering, because we have 10 minutes, okay, let's just start by explaining. And I see that we're doing it really fast, so on Wednesday, I'll also start talking about the coherence and so on. So we will be back on track. Okay, so linear systems, they are called systems, and they are kind of functions, but in a new way. I don't know if you ever played it. That do you know Charlie Chaplin movie called the one that he works in a factory?
Mm.
Do you know that he has like
It's
he needs
Time of
to
the world, or something.
yeah. Modern time.
Modern time.
Yes. So systems are like this Charlie Chaplin caricature that he just has the same problem. He needs to do again and again. He does like this with the Allen keys, right, or something like that. So you just have the same input, and there goes the same output, and just the system is doing again and again the same thing. So a system is a kind of a function. When you have a specific input, if it's a linear one, then it performs the following relation. So if you give it an x, like 1 or 2 or 3 or 4, then if you multiply the function by a scalar, this one equals to the function of the multiplied scalar by x. Okay? And it also fulfills the additivity. And the additivity means that if you have two numbers that are summed up together, then the system equals to the summing of each one of them. So let's see here an example. As you can understand, this is a very, very old material. So here we see the additivity. So let's say that we have these two inputs to the system, okay? And these two inputs, when you use it on this system, you have this output over here. When you use it on this system, you have this output over here. And then you sum the two of them together, okay? And this is the result of summing them together. And here you are doing a different thing. You sum the two signals together before they are entered into the system. And then you have a specific output. And then you ask yourself, is the output of this one equals to the output of this one? If so, this is called a linear system. And now, another feature of a system might be time invariant. I think that Izal talked about it, right? Now, time invariant means that the system is independent on time. So let's see, for example, if we have this signal and it is entered to YT and then shifted in time, this is the result. And here we have this system, which is already shifted in time. And when it enters this system, it equals to another output. And we ask ourselves, are they equal to each other? So let's say, for example, that we have this system, yn equals to xn plus n. And now let's use it at two different times. For n equals 1, and then n equals 2. And let's say that xn equals 5, okay? So here, when I put the n equals 1, then yn equals to 6, right? And if I use the n equals 2 and the xn equals 5, then yn equals 7. And these two are not the same. Therefore, this system is time dependent. Okay? So let's see that we fully understand it, and by so we finish. This is just kind of reminding you the definitions. So we have the amplifier neurons of Levis systemis function that have the following response function. Make it a bit bigger. So this is our function yt equals 2 of xt. So the neurons act as a linear system, a time invariant system, a linear time invariant system, or none of the above. So our system has an input and it just doubles it. Is this a time invariant system? No. Does it depend on time?
No.
It is true that the input is of time, but does the what the function does depends on the specific time that it is active.
No.
No. So therefore, it is true that this is a time invariant system. Is this a linear system?
Yeah.
Why?
It's linear function to exist. It's linear function. Doesn't it?
It's true that it is a linear function, but let's have.
Doesn't it enough to say that 2x is a linear function?
Yeah, it is also true, but when we show it, we need to stick into the definitions, right? So let's take x of t and multiply it by 3. And when we enter this, when we put the x of t multiplied by 3, then it's like multiplying y of t, right? And if we have two x's, 1 and 2, and both of them are in brackets, and they are entered into the system, it's like summing up two different systems. So it is true that this is also linear and also time invariant, so therefore this is a linear time invariant system.
Can you repeat why it's time invariant?
So let's see. So let's say that x of t equals to the number of 1, right? Therefore, y of t equals to 2 doubled by 1. So we can see here that it is independent on time. It just takes the same output. It doesn't matter if this output is now or later. It is always the same. How does a time-dependent system looks like. It has to contain, for example, 2x plus t squared.
Okay.
So this one depends on time because there is a variable of time in it.
Okay.
Okay? Great.
But
So,
what happens if x equals another number, let's say 2? We will have different outputs, no?
so let's say, for example, that y of t equals 2x squared. Is this one a linear system? No, right. Why? Because if I have an impulse of x1 plus x2, then the y of it is x1 plus x2 squared, right? But if I have y of x1 plus y of x2, this one equals to x1 squared plus x2 squared, and they are unequal to each other. Therefore, this is not a linear system.
No, they will be, so basically, time invariant doesn't mean that the output will be different, but what happens?
Yeah, it depends on the time of being here. Okay, so on Wednesday, I will talk about the response. And I'll bring some more exercises about filters and designing filters, so it will be a bit more clear. And we'll start also with the cross-spectral analysis. Okay? Great, so see you on Wednesday. Thank you. Okay. Dios, ahí va clase,